All right, so in the last lecture, we defined limits of complex functions, and now that we have limits, we can talk about the next obvious thing, which is derivatives. So given a complex function, f with some domain g, which lands in C, and remember G is just some subset of C. Okay, so for some point in the domain of f, define the derivative, which will use the usual notation f prime of z naught. Define this to be the limit as z approaches z naught of the difference in the outputs, f of z minus f of z naught, divided by the difference in the inputs, z minus z naught. Okay, so this definition looks exactly the same as the definition of the derivative in the usual calculus. But again, there's a lot more going on here because these are complex numbers. So the first thing is, notice that it doesn't quite make sense to think of this as the slope because these are complex numbers. In particular, we're dividing by a complex number. So this is no longer an expression for rise over run. There are geometric ways to interpret this, but maybe I won't get into that right now. And again, just like with limits, I mean, this is a limit. So another thing that makes this different than in usual calculus is z, again, can approach z naught from many different directions and in many different ways, right? And so this expression, as z approaches z naught, it has to be the same no matter how you approach z naught. So for any of these paths, you have to get the same expression here in these parentheses here. So that places strong constraints on when the limit's going to exist. In other words, this limit is less likely to exist than it was for functions of real variables. Another way to write this is if I just think of z as z naught plus h for some h, so h is sort of the difference between z and z naught, then I can express this as the limit as h goes to 0 of f of z naught plus h minus f of z naught divided by, well, z naught plus h minus z naught, but that's just h, right? But again, you got to keep in mind that h is a complex number here, so it's approaching 0 from many different directions. Okay, so that's the definition. Now let me give you some terminology. So as usual, if this limit exists, then we'll say f is differentiable at the point z naught. And it turns out to be really useful to introduce the following concept. So that was the first definition. If f is differentiable, not just at z naught, but for all points near z naught as well. What do I mean by near? I mean sort of arbitrarily close. So if f is differentiable for all points in an open disk, some small open disk, doesn't matter how small, but if there is an open disk where f is differentiable for all points in that open disk, let's say the disk is centered at z naught, then we say that f is holomorphic at z naught. So this is a new concept in complex analysis. Turns out to be really useful. Okay, so if E is an open set in the domain of F, then if F is holomorphic, at all points of E, then we'll say that F is holomorphic on E. Oops. We have class soon, I guess. Okay, and then finally, again, this is just language. We say F is entire if, this doesn't need to be capitalized. F is entire if, first of all, F is defined on all of the complex numbers, so its domain is all of C, and if it's holomorphic everywhere. So if F is defined and holomorphic on all of C. Okay, and that's just saying that it's differentiable at every single point in the complex plane. Okay. I don't want to make this video too long, so I encourage you to read the section yourself. There's a lot there. This is section 2.2, I believe. But let's just go through a few examples of functions and see whether or not the derivative exists. So, the first example that you want to look at is polynomials. And let's just do a simple one, f of z equals z squared. So hopefully this is going to be differentiable, because this is, almost the simplest function I can come up with. So let's check. So is this differentiable at some z naught? Let's see. Okay, so the definition of the derivative at z naught is the limit as, do it this way, so the limit as z goes to z naught of z squared minus z naught squared over z minus z naught. And I can factor the top. So I've got the difference of squares, so this is equal to z minus z naught times z plus z naught over z minus z naught. Okay, and as long as z is not equal to z naught, which it's not, because when you look at the limit, you're looking at points which are near z naught, but not actually z naught themselves. So in that case, the denominator here is non-zero, which means I can cancel these two terms. And so this is just equal to the limit of z plus z naught as z goes to z naught. This is overkill, but using rules of limits from the previous section, I've got a sum here. I can break that into, two limits. The limit of the sum is the sum of the limits, as long as they both exist. And this is pretty straightforward. So this is a constant function. It's z naught's a constant that we've fixed. So that's just z naught. And this is, well, what happens as z approaches z naught? Well, z approaches z naught. And so at the end, what I get is 2 times z naught, which is the familiar expression for the derivative of z squared. So we get the same formula as in real analysis for this derivative. But just to show you that weird things can happen now that we're in complex analysis, I'll give you another really simple function, but where the derivative doesn't exist. And the book has a few other examples of this as well. let's let f of z be equal to the real part of z. Okay, so in other words, z is a complex number, so it's some x plus iy, and I'm defining f of z to be the real part, which is just x. Seems like a pretty innocuous function, but let me show that it's not differentiable. And okay, what I'd like to do is I'm gonna make a mistake on purpose and show that it actually is differentiable, and then let's see where the mistake was. So I'm going to use the second expression here, this one, for my limit. So this is the limit as h goes to 0. So I've got f of z0 plus h. So the real part of that is x plus h. So I have x plus h on the top, minus f of z0. Oh, I should say x0, minus f of z0, which is just x0. So x0 plus h minus x0 divided by h. The x0's cancel, and so I get the limit as h goes to 0 of h over h. But h is non-zero. Since we're looking at the limit, we're looking at points near 0, but not on 0. So this is just equal to 1. Okay, so I've shown that the limit here is equal to 1. The question is, so I'm claiming that I made a mistake here. And the question is, where is it? So maybe pause the video for a moment and see if you can spot the mistake. But this is false. This part here. I claim actually that the limit does not exist. And the mistake was right here. And it really came from forgetting that h is a complex number. So remember, h is just some number in C, right? So maybe I should write it more carefully as a complex number. I can write it as, let's see, I'll call the real and imaginary parts h1 and h2. So h is equal to h1 plus I times h2. Okay, in that case, now let's see. So f of z0 plus h is what? It's the real part of the sum here, which is the sum of the real parts. So it's going to be equal to x0 plus h1. And this is really going to mess things up. So now let's look at this limit here. So we're looking at the limit as h goes to 0 of x0 plus the real part of h, which is just h1, minus x0, divided by all of h. So all of h is h1 plus, it's the real and the imaginary part, h1 plus ih2. So we can simplify the top still. The x0's cancel. So this is just the limit, h goes to 0, h1 over h1 plus ih2. And let's try to simplify this. So if I'm dividing by a complex number, I can simplify the expression by multiplying by the conjugate. So if I multiply top and bottom by h1 minus ih2, this is equal to the limit. In the denominator, this just becomes the modulus of h squared. So this is h1 squared plus h2 squared. Now I have a real number in the denominator, so it's a little easier to think about. In the numerator, I have h1 squared minus I h1 h2. Okay, so I claim this limit doesn't exist. And again, it's because we can look at different paths as h approaches 0. So this is the limit, h goes to 0 of h1 squared over h1 squared plus h2 squared plus I times the limit as h goes to 0 of h1 h2 over h1 squared plus h2 squared. Yeah, so I would just encourage you to look at different paths and convince yourself that the limit doesn't exist. So let's look at this expression first. So if I look at a path which is purely imaginary, so if I choose a path going to 0, where h is imaginary, in other words, h1 is 0, I just have the imaginary part, then let me label this star, then star equals 0, right? But if I choose a different path, let's say purely real, it's the simplest one, with h real, so that means h2 is equal to 0, right? Then star is equal just to h1 squared over h1 squared, which is 1. And so you see that for different paths, I'm getting different potential limits. Since they don't agree, this doesn't exist. And you can check that this part, same problem happens. If I choose different paths, I'll get different values for that limit, and so the limit doesn't exist. Okay, and so this is a pretty simple function, which already is not differentiable. And so that should convince you that there's more going on here. We have to be pretty careful. One other example, which I'll leave as an exercise. This is sort of another incredibly simple function, just the conjugate. See if you can figure out if this is differentiable or not. If you want to keep your life simple, first try it at z equals 0. And okay, that's it, but we'll talk about this stuff more in class.